Traveling the galaxies of knowledge, there are many perspectives. We marvel at the behavior of nature, more predictable or less. We look to our own lives, our actions, and what we make to improve life, to satisfy, fulfill. Behind these doors of perception, the explorer can strive to uncover the real nature of matter, and so enlighten what we are, change what we do. It is a fascinating journey, this path of knowledge, and the vehicle we ride is a science called chemistry.
Look at the incredible variety of things around us. The steel, the glass in this building, people sitting at tables, eating food, dressed in colorful clothes. These things don't just happen. People have made them. The fabric here is a blend of natural cotton and synthetic nylon. Even the colors that we see are due to a mixture of natural and synthetic dyes. You know, that range and intensity of color was just not available to ordinary people 100 years ago. This world has been transformed and changed by people experimenting and reasoning out how matter is built and applying that knowledge. What we have learned is that absolutely everything is constructed of groups of atoms called molecules. The science of molecules and of their transformations is chemistry. That science is largely responsible for the world that we have made.
Chemistry, the central science. Always at the heart of life itself, it's become central to our way of life. At the heart of cars and homes and what we enjoy in them. Take your car. It's here in the metals and in the paint that protects them. It's in the gas that makes it go, in what comes out the other end. It's in the plastic panels in our future, in the future cars themselves. We drive down chemical asphalt roads, work in chemically set cement structures, and live in homes which are commercial symphonies to chemical synthesis. Cleaners come in plastic containers. So does food, and garbage goes out in them. Each plastic bends, or shatters, stretches, or bounces because of its submicroscopic design. Chemical tailoring makes us fireproof, even bulletproof. We take for granted these products, rarely ask the why or how of the amazing new world we've made. But behind each plastic or pill, each paint or perfume, or dress or drink, lies a story of invention, of creativity. Working from his woodshed, Wilson Greatbatch would prolong lives with the heart pacemaker. Yet there was a further challenge for chemical innovation.
We were still only getting 1 to 2 years out of pacemakers, 2 years average. And the failure mechanism was always the battery. It didn't just run down, it failed. We finally wound up with this lithium battery. It really revolutionized the pacemaker business. doctors have told me that the introduction of the lithium battery to pacemakers was more significant than the invention of the pacemaker in the first place.
The invention came from knowing the special properties of the element lithium. From that early medical use, its applications have broadened into a major business, a longer life battery for a variety of consumers. Keeping well is a multi-billion-dollar molecular business. Molecular because a change in a molecule can mean the difference between health and disease.
At the base of most of our diseases is some molecule or molecules that are not working the way they should. And that we can actually find detailed atomic reasons why something is not working the way it should.
Probing deep to the molecular structures of plants and funguses can lead to new medicines, to cures for major diseases.
You have to isolate the active component, purify it, determine its structure, and then it gets handed over to the pharmaceutical people who decide how to package it.
I can't believe I ate that whole thing.
You ate it, Ralph.
Even if you're feeling just a little ill from a small overindulgence, perhaps, there's a wide choice across the counter.
Take 2 Alka-Seltzer.
All antacids neutralize acid. And if they're given in sufficient amount, any antacid is as good as another at neutralizing acid.
Explore chemistry, and you touch every aspect of sickness and health. Of course, what goes into the body in the first place matters a great deal. It all starts out with what is spread on the fields, how plants and animals grow. And at the end of it are foods and fats and oils, where some are better than others for your body.
It is better to eat more bent molecules than straight molecules. Generally, the recommendations are that we reduce overall consumption of fat and that we carefully control the amount of straight molecules, saturated fatty acids that we consume.
You'll discover how food can be preserved from supermarket to space, so you can eat at any time, any place. And then there are the flavors, mirages of taste.
You can mix together 20 or 30 chemicals, smell them, and it smells like a peach or strawberry, and it's seen nothing but a test tube. This is terrific.
Here is a world of subtlety, of personal preference, flavors, and fragrances, the secret world of perfumes, where a delicate nose commands the highest salary. There is personal chemistry in personal care. This substance isn't manufactured. It's a molecular covering for our molecular bodies. It's skin, and it changes chemically in the sun. We tan or burn. Scientists have designed new molecules for protection, constantly testing which sunscreens work better or won't wash off in water. There's beauty in chemistry, and chemistry in beauty. Roots of science down to the roots of your hair.
Kelly, I think you're going to find this so easy to take care of. See what happens when you have your disulfide bonds broken?
It looks great.
There's an art to science. Observant eyes, hands delicate and decisive, minds ordered and creative. Inventing products needs imaginative approaches.
The biggest part of a problem and the easiest way to solving a problem is to understand it. Have the problem in a form that you understand what's going on.
Brother of artist Andrew Wyeth, Nat Wyeth's creation was the plastic bottle. And his quest continues. Millions of bottles can grow into mountains of garbage.
One of my dreams is that we're going to be able to melt these bottles, the return bottles, melt them down, mix them with reinforcing fibers, and make car bodies out of them. And that when the car has served its purpose, rather than put it on a junk pile. Melt the car down and make bottles out of it.
Matter is neither created nor destroyed, but in industry we transform it every day. In this plant, the matter, the petroleum raw material, is being changed on a giant scale. Coming out of the plant are methane, ethylene, steam, and smoke and flame. But when everything is added up, the mass coming out will always equal the mass going in. Most of our raw materials are drawn from the earth, and that's where most of the products and waste end up too. The great challenge now is to clean up the mess we've made and reduce its production in the future. In between input and output are the huge factories built to make those products we know so well. Each of them comes from something and something else. This must be added to that, very accurately and on a huge scale. And this is where the captains of industry work.
You really have a huge network from the raw materials, which are primarily petroleum, to the refinery situation, which is primarily the place in which you get the starting materials. Then those starting materials are then used to make petrochemicals. The petrochemicals then are used to make all kinds of things, from plastics to medicines to drugs to whatever. I would guess that if you looked at it, probably 25 to 40% of the population of the country, in one way or another, is probably dependent upon that infrastructure.
Amidst the pipes and towers, the energy and precision, there is still the excitement of science well done. A breakthrough here in chemical fibers for carpets and fabrics is good cause to let everyone know.
I clearly remember the rockets went off in the hallway. Our research director had a way of, for every significant research achievement, setting off some rockets in the hallway, at which point everyone in the laboratory was alerted that a eureka had in fact occurred.
And the competition knows it too.
When our plant came on stream, acrylonitrile was selling for 28 cents a pound. We were making it for 14 cents a pound, and we shut down every other commercial process.
Within the secretive world of industrial research, you'll discover exotic substances. The liquid in this container is worth $350,000, a catalyst. The thin gold coating here is for missile guidance systems. And this intricate operation lays down the materials of computer circuitry, the chemistry of information. Even in basic steel and in the bags of rare ingredients that are thrown in to make alloys, there's plenty of chemistry.
I'm still accused of being a witch doctor, so to speak, with the little pinches of this and the little pinches of that. But we do know what we're doing.
If you really want to know what makes things work, there's a home for you here in the heart of science, in chemicals and chemistry. In fact, chemists are not just involved in making things, they're even more involved in discovering nature. What's there in the natural world? And what makes it change? They observe at the bottom of the oceans as new minerals pour from cracks in the crust. They ponder the order and symmetry in the rocks and minerals around us, the exquisite forms of crystals reflecting the shapes of atomic groupings beyond what the eye can see. Inquiring minds vault from our planet to others, to the mysterious moons of Jupiter, wondering why their chemistry is so strange. The mysteries of space abound, and sometimes fall to Earth.
Carbon-containing objects from outer space. What does it mean? Does it mean there's life out in outer space, and this represents a planet like Earth that developed life and then blew up or hit into another object, and these meteorites are relics from this?
Yet the greatest mysteries are right here on planet Earth, deep within life itself. There's plenty here to challenge searching minds for decades to come. What is the chemistry that makes the human being a molecular being?
How does a cell take sugar and convert it into a substance which is a storehouse for energy? Why is it that when I eat something, that helps me think differently? So in respects, but chemistry really is involved in how nature actually takes food and converts it into thought.
There's still so much to learn. I mean, my goodness, the thought of things that takes me years to do, nature does in a matter of seconds. The secrets there still have to be unraveled.
For the explorers of natural molecules, proteins, for example, discoveries can come at unlikely moments after fruitless years of searching.
I had a cold. I was lying in bed for 2 or 3 days. So I said to my wife, bring me a sheet of paper, and I think I'll work on that problem of how polypeptide chains are folded in proteins. So she brought me a sheet of paper and a slide rule and a pencil, and I started working. Well, I succeeded. It only took a couple of hours of work that day in March of 1948 for me to find the structure called the alpha helix.
The spiral that led to a Nobel Prize. Beyond drawings, today's microscopes take us to see, for the first time, atoms.
It was about 2 or 3 o'clock in the morning, and I was staring at this image, and I started to notice this regular pattern appearing, which I knew had to be the positions of the atoms. And it just got better and better, and I was just elated. Eventually, just tears came to my eyes because I was so happy having worked on this day and night for so long.
This is not a real image of atoms. It is a model of particles in a gas. Scientists often use computer-generated models to study structures in the submicroscopic world. This is ice, water molecules linked together in hexagonal shapes. On warming, some of the bonds break and there is liquid water. Heat still further, and the water molecules fly off to become a gas. Here is an atom of silicon, surrounded with 4 oxygen atoms in a tetrahedral shape. Attach many such tetrahedrons together, and we have the building blocks of silicates, the most abundant minerals on Earth. The computer can model the structure of silicate chains, as in asbestos, or silicate sheets, as in mica. It's the same with compounds of carbon. Quite simple molecules link, again and again, to form long chains, polymers. Models can graphically depict how 2 molecules, apparently identical, are really different, mirror images of one another. A vital realization in understanding the molecules of life. Using computers, scientists can begin to figure out how chains of proteins might fold up to become globular, intricate enzymes which govern the activities of our body's cells. The most beautiful and complex structures can be displayed, like DNA, the spiraling miracle at the core of life. But we want to go even further, explore beyond the wondrous architecture to visualize the dynamic actions and reactions of the molecular world. A few particles in a gas collide and bounce away unchanged. Even fewer collide head-on, react. Chemistry is about reactions. Here on a surface, a two-atom molecule separates. The molecule of another substance arrives and also separates. Different atoms then bond together and a transformation takes place. A new substance is formed. And from the very simple to the most complex interactions between drugs and the marvelously intricate molecules of the human organism. Scientists tailor pharmaceuticals with computer tools to probe how their designs fit with those of brain and body, blocking unwanted effects, enhancing desired activity, searching out what makes it all work. How do we make sense of this extraordinary world of nature, of industry, of products? We can take this world into the laboratory, observe, experiment, test the ideas that underlie it all. Right here is the key to chemical revelation. Meet the wizard of the lab, Don Showalter, professor of chemistry. Glasses on and stand back. Dramatic indeed. But each of these reactions between substances illustrates a concept of the way matter behaves. Some reactions are more tranquil and beautiful. Here, between aluminum and bromine. And here, from sodium metal and chlorine gas, Don is making simple salt.
Oh, it looks quite different.
From iron oxide, you yourselves can make iron.
Should see some of that iron. Look at that.
And you can even make aspirin.
I weighed out 138 milligrams of salicylic acid. And then the other active ingredient is acetic anhydride. And then we need to heat it for 5 minutes at 90 degrees. What I have to do is to get cooler. Oh, here it goes now. Look at that. See that cloudiness now turning into a more and more dense mixture now, so the aspirin is precipitating out of there. Now, there's the aspirin we made. Let's see if we can scrape it onto here so we can get a good look at that. That's acetyl salicylic acid. Well, we did it, but I'm sure glad I don't have a headache now, because we have just made about 1/3 of the acetylsalicylic acid that is in one aspirin tablet.
Sometimes observations alone are vital, on the speed of a reaction, for example.
Not many bubbles. Wow, look at the bubbles. Look at the smoke. Put it in there and presto, nothing happens.
Energy changes are important too. We can put in energy with heat.
Oh, here we go. Here we go.
Watch energy given off spontaneously.
Whoa, look at the flame.
Observe energy taken in, absorbed.
Whoop, look at this. The beaker is frozen to the bore. Look at that.
All in all, the excitement in the lab is almost electrical, enough to make, yes, you guessed it. This, then, is our journey through the world of chemistry. Experiment and observation guide the voyage, revealing the wonders of architecture unseen. We transform molecules to our will and pursue the infinite search for nature's truth.
The plant world is green, all shades of green. What I'd like to know is how these plants take carbon dioxide and water and sunlight and transform them into amino acids and carbohydrates and the oxygen that I need? Well, I can look at a leaf and zero in on a chloroplast, which is where the action takes place, and isolate out the beautiful green chlorophyll molecules that trap the light. And if I look deeper, I see copper, manganese, iron atoms, all crucial to photosynthesis. It's a beautiful chemical chain, this business of trapping elusive, seemingly unsubstantial light and transforming, using the energy of that light, relatively simple building blocks into the kind of complex molecules that make this tree grow. People have found out how it works. Why? Because we're curious. It's in the nature of human beings to be curious about the world around us, about ourselves. This is the ultimate driving force in chemistry, to know. What we don't know, we may find uninteresting. Worse, what we don't know, we may be afraid of. As we learn more about the world, the more interesting, the less threatening, the more beautiful it becomes.
Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.